Hey guys, today we're looking at 4.2 day 2, which is continuing to talk about multiplying polynomials, but here specifically we're focusing on expanding binomials using Pascal's triangle and binomial theorem. So Pascal's triangle is this shape here that's kind of this honeycomb looking thing, where there is a pattern to how we fill this out. Now it's something that has a lot of different applications. But we're going to look specifically at how we apply this to binomial expansion theorem. So what I want you to do, take a second, go ahead and pause the video, and I want you to try and figure out if you can see the pattern in Pascal's triangle, which again is this honeycomb looking thing, where in the top we have 1, we have 2 1s underneath it, and then 1 2 1, 1 3 3 1. We've got some blanks here, 6 4 1. See if you can figure out the pattern, and I'm going to let you guys take a second to do that. Go ahead and pause the video. If you can figure it out, go ahead and continue filling it out. Okay. Hopefully you guys were able to figure this out, that as we look through this, kind of the far side are all just 1s in here. So as I continue down, make this a little bit bigger here. So as I continue down the far outside, all of these are just going to be 1s. 1, 1, 1, 1, 1, 1, 1. And then you can see the 2 above it add up to get the 1 below it. So here we have 1 plus 2 equals 3. And the same thing here. 2 plus 1 equals 3. 3 plus 3 equals 6. So we can kind of continue on down our pattern. Again, I'm going to go ahead and skip the video, or skip ahead in the video, so go ahead and pause it real quick, fill this out yourself, and then I'm going to come back in just a second, and I will have it already completed for us. Okay, so take a look and see, now that I have mine filled out, to see if yours matches. If you need to, go ahead and pause the video here real quick and make sure it's all copied down and accurate. We won't be using necessarily all of this triangle, but there is some relationships here between when we expand a binomial and Pascal's triangle. There's a ton of different applications and kind of different creative ways that you can look at and analyze and kind of color if you wanted to turn this artistically into some different pictures and stuff with Pascal's triangle. You know, if you colored or shaded all of the even numbers or all the prime numbers or all the multiples of certain things, there's some patterns in here if you want to get into some fractal math. Which is something that we look at kind of upper level stuff and different geometric stuff. But there's tons of different applications to Pascal's triangle. If that's something that interests you and intrigues you and you like looking at patterns, go ahead and Google Pascal's triangle, and there's tons of different applications and different ways of looking at it. But that's it for right now. We're going to continue moving on, and we'll kind of look at how this is applied in just a little bit. So getting into our first actual problem here, they want us to expand x plus 1 to the 4th power, meaning multiply x plus 1 to the 4th power. If it says expand, we're taking that single binomial to the 4th power and getting it all the way into just a standard form polynomial. So the way that I can do this, I've got a couple of different choices on how I want to go about expanding. I've got x plus 1 to the 4th power, which means I have 4 x plus 1s being multiplied together. So what I would suggest, kind of our method of how we do this, since there are 4 of them, I'm going to take and multiply 2 of them together at a time, and then multiply those 2 parentheses together afterwards. You also could take and FOIL together 2 of these, multiply the 3rd one in there, and then multiply the 4th one into that result. That's perfectly acceptable as well. But especially in this case, since we have the same thing to the 4th power, if I multiply 2 of these together, I know I get the same thing as multiplying the other 2 together. So I'm going to go ahead and do that here with my first 2. So you can do this either foiling or with box multiplication if you want to. But here, x times x gives me x squared. X times 1 is x. 1 times x is x. Not y. X. And then 1 times 1 is 1. So I end up with x squared plus 2x plus 1 when I multiply 2 of them together. And I know these 2 will give me the same thing, x squared plus 2x plus 1. So now I have to multiply that 3-termed polynomial with that other 3-term polynomial. And again, you've got your choice on how you want to do this. You could just go through and not really FOIL because it's not just 2-term things. But you could do distribution where you multiply your x squared into all 3 of the other terms. So if I wanted to do that here with some different colors, I'd multiply my x squared into all 3. I would multiply my 2x into all 3, and then multiply my 1 into all 3. So you can see that gets kind of messy. I prefer, when I'm doing more complicated equations like that, or complicated multiplications, to do it using the box multiplication. Couldn't remember what that word was. So here I've got a 3 times a 3 term thing. So I've got a 3 by 3 box, x squared plus 2x plus 1, x squared plus 2x plus 1. And then when I multiply going in my box, x squared times x squared is x to the 4th. 2x times x squared is 2x cubed. And then x squared times 1 is just x squared. X squared times 2x is a 2x cubed. 2x times 2x is a 4x squared. 2x times 1 is just 2x. And then the last one, x squared times 1 is x squared. 2x times 1 is 2x. 1 times 1 is 1. And then like I showed you guys yesterday, now we have kind of these diagonals of like terms that makes it a whole lot easier for me to collect up what I need. Because what we end up with now, if I put that all together, I ended up with x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. And that's our final expansion of x plus 1 to the 4th power. Now, where we use, or kind of where Pascal's triangle comes into play here, if we look at our coefficients of this final expansion, they were 1, 4, 6, 4, and 1. And if you look back up here, we actually have 1, 4, 6, 4, 1 as one of the rows in Pascal's triangle. And that's not by coincidence. Interestingly enough, these patterns, these rows, end up describing the coefficients when I expand a binomial. So a binomial, again, just meaning a 2-term thing, x plus 1 in our case is what we were looking at. When we expand that to different degrees, these are what my coefficients end up being. So when we applied something to the 4th power, we ended up getting this row, which means this one is going to be something expanded to the 3rd power, gives me this. This we know is something squared. No, I'm not going to put anything in that parenthesis. So on and so forth. So if we were looking at something where we were multiplying out or expanding binomial to a certain exponent power, we could utilize these coefficients to be able to write what those things are, which is what we're getting to on the back side here. So this top side of page, or the kind of the back side of your notes, this kind of strip here above where it says if we must expand a binomial, we can substitute into the above patterns for A and B. Everything above that on the back side here, that is going to be provided to you on your cheat sheet or your formula sheet on the quiz that you guys will take next Friday. Whatever that is, the 4th, I think it is. The Friday after Thanksgiving. So in here, there's a lot of information. And again, it's just kind of just showing my coefficient of Pascal's triangle. And these are my different degrees on my binomial. And here, this is going to be more generically my binomial as just being first term plus second term, a plus b, to whatever exponent we have. Now, some things to kind of look at pattern-wise. Now, this, again, this will be given to you, so you could always just look at it and be able to utilize it once you know what your A's and your B's are. But if you look at my pattern, my coefficients obviously follow Pascal's triangle as we've established already, with my, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, so on and so forth. Really, the 5th degree expansion is probably as far as we would go. But if you look at my variables, my a's and my b's, they kind of follow a different pattern. My a, the biggest degree that I have, is always that first term all the way to the left, and it goes in descending order as you move to the right. And my b's go the opposite of that. So I start smallest on the left side, and then I increase in my number of terms all the way to the right. So you can see here, like for my 5th degree expansion, my a to the 5th power starts all the way to the left. My b to the 5th power starts all the way to the right. And as you move in that other direction, so here for a, as I move in this direction, you can see my exponents on a decrease, because that's going to be a 1 there, all the way down to having a to the 0 power for my last term. But the opposite effect happens going in the other direction for my b values. They go in decreasing order as you move towards the left. So just, again, not anything you have to necessarily have memorized, but some patterns that pop up in what we're working with here that could make it a little bit easier for us. And again, this is a formula you're going to be given. You don't have to have it memorized, so don't feel like you have to try and memorize this. There's a lot of information and a lot of stuff to process. But the way that we would use this is by substituting variables in there, or things, terms in there for a and for b into the formulas that were given above. So in example number 1, if we're asked to expand x minus 2 to the 5th power, we are going to use this 5th row, right, because this is the 5th power. So this right here that I'm underlining is going to be what we use to substitute in with a and b based on what our function is. So you don't have to necessarily do this. I'm going to. Just because, again, like when we first started learning how to do like quadratic formula or any of those other formulas, I always start with just the generic term first. The more times you write it down, the deeper and deeper it gets drilled into your long-term memory. But here, I'm going to go ahead and write down what I'm substituting into. So 1 a to the 5th plus 5 a to the 4th b to the 1st plus 10 a cubed b squared plus 10 a squared b cubed plus 5 a b to the 4th plus 1 b to the 5th. Sorry for my handwriting. It is what it is. So that's going to be just that's for my formula. That's what I have underlined in blue up above. But in this one specifically, if it's supposed to be a plus b, in this, my a is x and my b is negative 2. So in that formula, anywhere I see a, I'm going to put an x value in there. And anywhere I see b, I'm going to put a negative 2. And that's going to allow me to expand it out without having to use the full distribution or foiling or anything for 5 different parentheses. So if I go ahead and do that and just substitute x for a and negative 2 for b, I end up with 1 times x to the 5th plus 5 times x to the 4th, negative 2 to the 1st. I'm going to have to use a smaller marker. Oh, I should have space. Let's go ahead and undo that. Well, redo that. Okay, that's that one. Plus 10 x cubed negative 2 squared plus 10 x squared negative 2 cubed plus 5 times x negative 2 to the 4th plus, move over just a little bit, 1 times negative 2 to the 5th. Just barely fits on that page. So once I have that substitution done, now it's just order of operations, just kind of simplifying stuff down as far as we can. So 1 times x to the 5th, well, that's just x to the 5th. And here you just have to be careful with your exponents, especially on your numbers here, because it's negative 2 that you're plugging in. So negative 2 to the 1st power is just negative 2, times that 5 gives me a negative 10 x to the 4th. And I just keep doing that. For my next term, I've got negative 2 squared is a positive 4, times that positive 10 makes it a positive 40 x cubed. Negative 2 cubed, so negative 2 to the 3rd power is a negative 8, times 10 is a negative 80 x squared. Negative 2 to the 4th power is a positive 16. 16 times 5 gives me another 80, but here it's going to be a positive 80, and that's just x. And then negative 2 to the 5th power is a negative 32. So we have that final expansion right there. X to the 5th minus 10x to the 4th plus 40x cubed minus 80x squared plus 80x minus 32. Now, that does seem tedious and it does seem time-consuming, but when you compare it to what we would have to do alternatively, in which case we would be having to take x minus 2, multiplying it together 5 times. Can't say the number unless I'm going to start doing it. That's 3, 4, and 5. So, I mean, yeah, we could multiply 2 of them together, and then I get the same thing with 2 of them together, but then I have to multiply that 3 by 3 together, and then I still have a 5th binomial you have to multiply in there, and you can just see, yes, it can be done, and technically, I don't think, I'd check and see for sure, but you guys have the study guide already for the quiz. I don't think I specify what you have to use for expanding it out. I don't think you have to use Pascal's triangle to expand it out in the instructions. I may be wrong on that. So technically you could just FOIL it all the way out just like we did on the front side and just like we did yesterday if you're comfortable with that. And sometimes that is more useful. Like if we look at this next one, obviously for example number 2, I'm going to show you how to do it using the Pascal's triangle, the binomial expansion theorem. But with something where it's just a cubed and you only have 3 of those parentheses multiplying together, you could go through and just multiply it the old school way. Just take those 3 parentheses, FOIL 2 of them together, and then multiply the 3rd one in there. That's perfectly acceptable. But in this regard, I'm going to show you guys what that looks like for, again, binomial expansion. So here we've got a 3rd power, so just copying from above, we are going to use 1a cubed plus 3a squared b plus 3ab squared plus 1 b cubed. And here a is going to be 3y and b is going to be positive 1. So 1 times 3y cubed plus 3 times 3y squared times 1 plus 3 times 3y times 1 squared plus 1 times 1 cubed. So here again I'm just plugging in 3y for my a value and positive 1 for my b value. Now you have to be careful with this next step here because you have to square, like because that a value was a coefficient and a variable, you have to apply the exponent to both of those things when you're going through and simplifying. So here 3y cubed is 27 y cubed because 3 cubed is 27, y cubed is y cubed. For my next one, 3y squared is 9y squared. So 9 times 3 gives me another 27y squared. Then we get into more simple ones as we go through this. Then 3 times 3 is 9y, because 1 squared is just 1, and then 1 cubed is just 1. So we end up with 27y cubed plus 27y squared plus 9y plus 1. Which again, that wasn't too horrible once you get a feel for them. They go through a little bit quicker once you kind of get used to the rhythm of how we do them. Especially after you do a couple of them of the same style, it does get easier. It's just kind of getting that practice in there. And again, you didn't necessarily have to do this, and here you could just take those 3 parentheses, FOIL 2 of them together, and then multiply the 3rd one in there. But here, 3 relatively simple steps. Yes, tedious steps, I understand, but simple nonetheless, and you got your answer. So that's all I got for you guys for this section. Where am I hiding the homework? There it is. The homework for 4.2 day 2 is page 171. You guys are just doing 43 through 48, but both evens and odds. So it's just going to be those 5 binomial expansions. And again, I want you to try binomial expansion theorem, this Pascal's triangle method that I showed you guys today. But on anything where it's like a cubic so it's like a cubed. You could use the old school method if you are just way more comfortable with that. But I do want you guys to try and give it a chance. See how it works for you. If you really don't like it after today, you don't have to continue using it. It's just kind of a shortcut for us. But it is something that I think is beneficial for you guys to be able to do, to save you guys some time. But that's all I got for you guys. So as always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. And have a fantastic day.